All the volumes that we have found so far involve solids that were filled in. By filled in, I mean that the axis of revolution lay along one edge of the area, so that when we rotated, it was solid. However, if it does not lay on one edge of the axis, then the volume of revolution may have a hole in the middle. So if you take a look at this example right here, here is my axis of revolution. And then the rectangular piece that I want to rotate is not lying on the axis, but it's above it. So when I rotate it, I get something that looks like this, kind of like a toilet paper roll. So now that when I cut a slice of this toilet paper roll, you're going to get a circular ring that looks like this. We often call this a washer. Now the area of such a washer is based on the area of the outer circle minus the area of the inner circle. So we can say this is going to be pi times r squared. So this is the radius of the outside, minus pi times r squared of the inner ring. So I can factor the pi and get r out all squared minus r in all squared. Thus, the volume of a typical washer is then going to be pi times r out squared minus r in squared. That would be the area of one washer. Then we need to multiply that by the thickness of that washer. So then, as before, we're going to integrate to find the total volume from the left to the right or from the bottom to the top. So if it's about the x-axis, we would say that the volume is equal to the integral from a to b, and that's going to be pi times f of x all squared, assuming this is going to be the outer ring, minus the radius, which is going to be, we'll call it g of x, the radius of the inner ring, and then dx. If we revolve about the y-axis, then our volume is going to be the integral from c to d, and then it'll be pi times f of y all squared minus g of y all squared, and then this will be dy, since we're rotating about the y-axis this time. So let's take a look at some examples. So this first one here, it says to find the volume by rotating the area contained between y equals x squared and y equals x around the x-axis. All right, so let's put a value of 1 here. So we're going to enlarge our scale a bit. Okay, so this first value picture is a parabola. So we have 0, 0, 1, 1, and then this would be 2, and then 4 way up here. So we know that it's going to curve quite a bit like this. The other function is a line like this. All right, so when we rotate this, I'm going to draw the symmetrical one, symmetrical part of it down here. And then this would be circular. So if you imagine this, on the outside it would be smooth, like a cone, but on the inside it would be kind of bulging into the inside, all around. So I like to find the radius of each of the rings. So the radius of the large circle, actually let's color code this too. So the radius of the large circle would equal a distance of y, and so in our case this is going to equal x. The radius of the smaller ring, let's say it was this one here, is also equal to y, and the equation of that one is going to be x squared. So we want to find out where these intersect, and from the diagram we can see that it's going to be at 0 and 1, but let's say that you didn't know that. So you can actually intersect the two equations. So we have x squared minus x equals 0 factor out the x, and then x equals 0 and 1, which is what we have. So to find the volume, it is the integral from 0 to 1 pi. So my outer ring is going to be x, and then squared, because it's pi r squared. Remember, the area of a circle is pi r squared. And then minus, the radius of my smaller one is going to be x squared, and we still need to square it as well. And this is going to be dx because we're rotating about the x-axis. So the volume is equal to pi, and I'm just going to simplify my inside here. So this will be x squared minus x to the 4 before I integrate. So then I get x cubed over 3 minus x to the 5 over 5 from 0 to 1. And then plugging in 1, I get pi 1/3 minus 1/5. So the volume is going to be 2 pi divided by 15 units cubed. All right, let's take a look at another one. So this time, let's revolve about the y-axis so you can see the difference. This time, the region is bounded by y equals x squared and y equals root x between 0 and 1. So again, I'm going to enlarge my axis. So I'll put 1 here, 1 here. And again, I have my parabola. And if you want, you can also pick half. And when it's half, you do get a quarter, which is right there. The other function is y equals root x. So we get 0, 0. And also 1, 1. So this time we get this part here. And we're going to rotate about the y-axis. So I'm going to draw the symmetrical piece on this side here. Okay, so you can imagine it's similar to what we did last time, but remember this is a parabola. So this is actually, it's like a cup or a bullet shape on the outside this time. This is what it's going to look like on the inside, but remember it's going to be bulging in on the inside. Okay, so again, we're going to do the same thing. We're going to find my large radius. So notice that my large radius is this distance here. Okay, so we're going to say that's going to be x. Now, because we're rotating about the y-axis, we need to write the functions in terms of y. So this was the parabola. So actually, it's going to be nice to write. So this is y equals x squared. So when I rewrite this, x is actually equal to plus or minus root y. We're going to just take the positive so that it's positive a value. The radius of the inner or the small ring will be this distance here. So we're going to take the radius of the large one, and then we can find the radius of the small one from here to here, which is also going to be x. And this is the equation of the second one. So this is going to be x is equal to y squared this time. So to find our volume, we're going to integrate, and this one we can see it's from 0 to 1 as well. And this will be pi. And my larger one is root y. My larger radius, we're going to square that, and then we're going to subtract y squared squared, so the radius of the smaller ring. And this will be this time dy. So the volume, we're going to factor out the pi, or bring the pi to the outside, and let's simplify each part inside before we integrate. So this will give me y minus y to the 4th. So then we get pi, and this will be y squared over 2 minus y to the 5 over 5 from 0 to 1. So we get half minus 1/5, and then when we plug in 0, we get 0. So the volume is this time going to be 3 pi over 10 units cubed. Okay. So notice how we always consistently find the radius of the large ring and then we're going to subtract it from, or subtract the radius of the small ring from that large one. And the reason that we're doing that was actually not just subtracting the radius, we're actually subtracting the whole entire area. Okay. All right, so let's take a look at the last example. And this one's a little bit tricky because this time we're going to rotate about the line y equals 3. And we have the region bounded by y equals sine x plus 1 and y equals 1 between 0 and pi. Let's begin by drawing the axis at y equals 3. And then we'll draw the y equals sine x plus 1 graph. So it's a sine graph, but it's moved up with a vertical displacement of 1. And we have y equals 1, which is another horizontal line right here. But this time we're going to rotate only between 0 and pi. So we're only going to take a look at this piece here. So when I rotate this, I'm going to get the other piece on this side over here. And it's hard to visualize this, so I'm going to try to make it 3D by drawing a circle or an oval here. So you can see this. So it's kind of like a spool of thread, but it's actually curved in on the inside. So just like before, I'm first going to find my large radius. And from the picture, you can actually just see that this is the large radius, which is 2. However, if I want to calculate this all the time, because sometimes it will be different, we can think of this as the distance from the x-axis, from the axis of revolution to the x-axis. So that is going to be 3. And then minus 1, because this is 1 here. So that will be 2. My other radius is this distance here. Okay. Now again, we can think of this as 3. And then we're going to take away this distance here. So the full distance is 3. If we take away this height here, this y value, then we'll be left with this radius. So that's going to be 3 minus, so 3 would be the total distance, taking away this y value here, this sine expression. We're going to have 3 minus sine x plus 1, which then gives me 3 minus 1, that'll be 2 minus sine x. So the radius of the smaller circle here is going to be 2 minus sine x. So writing the volume equation, I get the integral from 0 to pi, and then pi times the radius of the larger radius squared, so it'll be 2 squared minus 2 minus sine x all squared, and then dx. So simplifying this, I get pi, integral from 0 to pi, 4 minus, and this is actually 4 minus 4 sine x plus sine squared x dx. 4 minus 4 is 0, so I get positive 4 sine x minus sine squared x. All right, I'm actually not going to show you how to integrate this by hand. We'll plug this one into the calculator. A graphing calculator will do. One that can calculate integrals. And we get 6.429, and then still times pi. And when I do multiply by pi, I get 20.198 units cubed. So whenever you're doing any of these questions where there is a hole, I recommend that you try to find the radius of the large circle and then subtract the radius of the smaller circle. And both of them will be squared because you're going to factor out that pi, and so you're really just subtracting the radius of the larger squared minus the radius of the smaller squared.